Welcome everyone to our seminar today. So our speaker is Jintao Deng from Texas A&M University. So Jintao is going to tell us about the Novikov conjecture and group extensions. So please, Jintao.
Okay, thank you for your for the invitation, and it's my pleasure to give a talk in this seminar. Today, my title will be Novikov conjecture and group extensions. Actually, the group extension is I just consider about the extension of costally embeddable groups. Okay, before I talk about the Novikov conjecture, I would like to go through some motivations. Firstly, it's about the positive scalar curvature. So there is a question like if you have a Riemannian metric and you can actually define the scalar function, and so it's a very natural question to ask, if you have a prescribed scalar curvature, can we find a Riemannian metric with a given scalar curvature function? So there is a result by Kushner and Warner for the function. If you for the scalar function, actually this is a this is a smooth function. If you have the smooth manifold and a smooth function, if the function has a negative value at some point, then we can find such a Riemannian metric with a prescribed scalar curvature function. So the most interesting case is realizing the positive scalar curvature. So and usually it has global obstruction. So we have two methods to say the obstruction. So first one is actually by Sean and Yao. They solved the existence problem of the positive scalar curvature on N-torus. Actually, their method is called a minimal hypersurface method. And another method, I'm going to focus on another method, which is by Gumov and Lawson. So the baby version of it is actually the Nishikawa's formula on the index theory of Dirac operator on spin manifold. So if you have a Dirac operator D on a spin manifold, so Nishikawa's formula tells us that D square is equal to the Laplacian plus the 1/4 times the scalar function. The kappa is a scalar function. So if we assume the scalar function is bigger than some positive constant everywhere, then we'll say D is actually invertible, because here the Laplacian is positive. So the positive plus the positive operator plus you can view this as a multiplication operator. So it will give you the D square is actually invertible. So a result that D is also invertible. And by the index theory, the Fredholm index of D is defined by the difference of dimension of kernel D and the dimension of the co-kernel D. Because D is invertible, so this number is 0 and this number is also 0. As a result, you'll have the Fredholm index of such a Dirac operator is 0. And if we know, so which means if we want to find a obstruction to the positive to the positivity of the scalar function, we actually can compute. We actually can compute the index of D. If the Fredholm index is not equal to 0, we will have that it's an obstruction to the positivity of the scalar function. And by the Atiyah single index theory, the Fredholm index of D is actually given by the A hat genus, and A hat genus is a topological invariant. So theoretically, this is computable. Therefore, we have a machinery to determine if the manifold the smooth manifold has a Riemannian metric with positive scalar curvature. So by usually the A hat genus always vanish in many cases. So we need to find a better invariant. So it is called the Hell index. So what is Hell index? before I talk about the Hell index, let's talk about some a conjecture by Gromov and Lawson. So it claims that an aspherical manifold does not support any positive scalar curvature. So aspherical means the universal covering of the manifold is contractible. So here we can follow this this machinery by the Nishikovic's formula. So here we can consider about the fundamental group of the manifold, and we can actually lift the Dirac operator on D to the universal covering. So here because the ellipticity is local, so we all know D tilde is elliptic, but the problem is in the case when gamma is infinite, we know the lifting Dirac operator is not Fredholm, so we cannot define the Fredholm index of D tilde. So we need to generalize the definition of the Fredholm index. So we can define the Hell index and the Hell index of D tilde, but the Hell index is not an integer. So it's actually an element of some sister algebra, which is called the equivalent rule algebra. I will define this sister algebra later. So which means we care about the Hell index of the of such a lifted the lifting of the Dirac operator. So because if we go back to this baby version of the Gromov-Lawson framework, so in the universal covering, this is also this formula also holds. So which means that if we go through all this machinery again, we all know the non-vanishing of the Hell index. Hell index is also an obstruction to the existence of positivity of those of the Riemannian metric. So which means we really care about we should find some machinery to compute the Hell index. So if you want to compute the Hell index, at least you need to understand the K-theory of the sister algebra. So, but there is a difficulty. This sister algebra usually is very hard to compute. Let's say why it's hard to compute. So usually if you have a sister algebra, so how do we compute the K-theory of the sister algebra? We usually we need to find some ideas. We need to find two ideas of the sister algebra, and then we will have a six-term exact sequence. It looks like K0 of I intersection with J to K0 of I direct sum with J to the K0 of A and to K1 of I intersection with J, and the sum of the K-theory. And so if we have the sister algebra with very nice structure, by nice structure I mean it has a lot of ideas. So if you can understand the K-theory of those ideas, so by the Melville-Torch sequence and 5 lemma, you can understand the K-theory of the sister algebra. So, but the problem is this, I'm not telling you the definition of this sister algebra now, but I'm going to tell you this sister algebra is global. So in other words, it does not have many canonical ideas. So as a result, you will say it's very hard to compute in practice. But usually if we cannot compute the K-theory, we actually worry if we can determine if the Hell index is 0 or not. If we can, because if we go back to the machinery here, if we can determine the Hell index of D tilde non-vanishing, we will say no positive scalar curvature Riemannian metric on M. So which means the non-vanishing is good enough. So we actually need machinery to determine if it is vanishing. So we actually can define an assembly map, and by the assembly map, by the injectivity of the assembly map, we will determine if the Hell index is vanishing. So now let's so this is the injectivity of the assembly map is actually strong Novikov conjecture. Okay, so now let's look at a possible algorithm to detecting non-zero Hell index. So we have a commutative diagram. So here, this is topological data, and this is the key theory of the system algebra we care about. And if you have any lifting Dirac operator, you can take the Hell index, and it takes value in the key theory of this guy, but it is hard to compute. And actually, we can find a reference map to push forward the lifting Dirac operator to some Rips complex, and then we will get a class in the key theory of the localization algebra. And because this guy, the advantage of this guy is easy to compute. So which means the Hell index is very compute in this key theory, but it's pretty easy to compute in this key theory. And if we know, so if we can determine it's non-vanishing in this key theory, and plus the EV star, the assembly map is injective, then we will say the Hell index is non-vanishing. So this is the reason we care about this assembly map. And the strong Novikov conjecture says if you consider all the scale of the Rips complex, and you will have the assembly map is injective. This is strong Novikov conjecture. So actually we are going to use just like a black box. The strong Novikov conjecture implies the Novikov conjecture. So in my talk, I will consider about the strong Novikov conjecture under the group extension. So let's talk about what is Novikov conjecture. So before I talk about Novikov conjecture, let's look at the Borel conjecture. So among the aspherical closed manifold, two manifolds are homotopy equivalent, imply their homeomorphism to each other. So aspherical, as I explained, aspherical means the universal covering is contractible. So the Novikov conjecture is actually an infinitesimal version of the Borel conjecture. So the Novikov conjecture claims that the Hell signatures of compact manifold, compact-oriented smooth manifold are invariant under orientation preserving homotopy equivalence. So actually the Hell index is defined by the Riemannian structure, but Novikov proved that they are homeomorphism invariant. Okay, so here to be precisely, I will it's a deep result by Novikov. He proved that the rational point-reacting classes are invariant under homeomorphism. So the Hell signatures is actually generated by the rational point-reacting classes. So in the case of aspherical manifolds, the Borel conjecture implies the Novikov conjecture. And also following the work of Mishenko and Gasparov using the signature operator in place of Dirac operator in Hell index machinery, we will have the strong Novikov conjecture implies the Novikov conjecture. Okay, and actually we have already know in many cases the Novikov conjecture holds. So the remarkable one is by Professor Yu in 2000. He proved the Novikov conjecture holds for coarsely embeddable groups. I will explain what's the meaning of coarse embeddability later. And also a paper, by a recent paper by Roman Tesser and Shintaro, they proved that Coarse embeddability is not preserved by under group extensions. So which means if you have a group extension of Coarse embeddable groups, you have the normal subgroup and the quotient group, both are Coarse embeddable, but we don't know if G is Coarse embeddability, which means in this case, we cannot use, we cannot apply the result by Professor Yu. So, and also in 2001, Oyuno proved that the Baum-Connes conjecture is actually preserved by group extension. Actually, there are some extra requirement on the quotient group. So we maybe the easiest case is if the quotient group is torsion free and it satisfies a Baum-Connes conjecture and unsatisfied Baum-Connes conjecture, then G satisfies Baum-Connes conjecture. And also we also need I should say the Baum-Connes conjecture with coefficient here. So you have to consider about the coefficient. But this already covers a lot about the case for the Baum-Connes conjecture. And but in Novikov conjecture, there is no such similar extension result for the Novikov conjecture. So it's very natural to ask if you have the extension of Coarse embeddable groups. It's very natural to ask if G also satisfies the Novikov conjecture. So now let's talk about the geometry of groups. So if you have a finitely generated group and you fix a finite symmetric generating subset, so we can define a word length metric function on the group. It was defined by the shortest length of the decomposition of your element by the element in the generating subset. And then we can define a left invariant metric. Just take the length of the distance of two elements is actually the length of the multiplication by G inverse times G prime. So the example for the a good example for the for this matrix is you can consider about the integer group. This is an abelian group, and the generating subset is given by -1 and 1. So in this case, the metric is just the absolute value of the difference for any pair of integers. So now if we are giving a finitely generated group, then we will have a metric, left invariant metric. And now we can consider about the geometric properties of this group. So a very important concept of the geometric group is Coarse embedding. It was introduced by Gromov. So if you have a group with a metric we defined before, so it is called Coarse embeddable if you can find a map from the group to the Hilbert space, and with two increasing control function rho plus and rho minus, you have the limit of rho minus t goes to infinity as t goes to infinity, and the distance between the image of any pair is controlled by rho plus of the distance of dx and y, distance of x and y, and rho minus of distance between x and y. So this is Coarse embeddable. So Coarse embeddable, roughly speaking, Coarse embeddable means just like a people stand in front of a mirror. Maybe the mirror is a little bit, it's a little bit twisted. So you will get a very not precise image, but we have some control on the twisting of the mirror. So roughly, so you will have the big picture of the object in front of the mirror. So we actually do not care about the tiny details. So this is the meaning of the coarse embeddability. And the examples of coarse embeddable groups are amenable groups and amenable groups, and a group with probably A, which was introduced by Guoliang. So my main result is if you have a short exact sequence of countable discrete groups, and both N and G module N are coarse embeddable into Hilbert space, then the Novikov conjecture holds for G. So even though we don't know the geometry of the G, we don't know if it is coarsely embeddable or not, but we still can show the Novikov conjecture holds for G. So this is our main result. Any question? Okay, let's move on. So now let's define what is Novikov conjecture and Baum-Connes conjecture. So if we fix a scale D, and a Rips complex at scale D is denoted by PD gamma, and it's a simplicial complex, while the set of vertices is gamma, and a finite subset spans a simplex if and only if any two element of the finite subset has distance smaller than D. So this is a Rips complex, and for each Rips complex, we can have a metric which is proper, and also if gamma is a group, and you will have a simplicial action of gamma on the Rips complex, and under this case the metric is proper and invariant. And also, in order to define the row algebra, we for each D, we will choose a countable gamma invariant dense subset ZD of the Rips complex, and we require ZD is contained in ZD prime when D is smaller than D prime. So so now let's introduce some geometric concept. So firstly, we fix a separable infinite dimensional Hilbert space with trivial gamma action. Gamma is a group. So define a Hilbert space, define the tensor product of those three Hilbert space with a tensor action. So gamma x on this amount on this part is by translation, and on this part is trivial, and on this part is left regular representation or left or regular translation. So so every element on this Hilbert space, because this is countable. So for every element every bounded operator on this Hilbert space can be read as a matrix. So T can be read as a matrix, and this is XY is in ZD, so it's ZD by ZD matrix, and this is the reason why we want a ZD is countable. So the propagation of such a operator is defined to be the sup of the distance between YZ such that the entry on YZ is not equal to 0. And if for an element, if such a quantity propagation of T smaller than infinity, we will say T has finite propagation. So actually, it's just like a matrix was defined. Matrix was defined on some strap with finite width. So here, the width of the strap is actually the propagation. So this is the meaning of the propagation. And the locally compact means, roughly speaking, it means each element is compact, and also with some more requirement. And an element is said to be gamma invariant if it commute with the group action of gamma. So if we consider all these geometric concepts, and we will have a system algebra, which is called a row algebra. So sometimes it's also called by equivariant row algebra. So this is generated by all finite propagation, locally compact, and gamma invariant operators on this Hilbert space. So so this system algebra is actually quite global, and it does not have too many canonical ideas. And the localization algebra is defined by the system algebra of all the universal, continuous, and bounded function from the half-real line to the row algebra with propagation goes to 0 as t goes to infinity. So because of this propagation condition, it makes the K-theory of this localization algebra is quite quite topological. So in some sense, the K-theory of the localization algebra is computable theoretically. And then there is a natural evaluation at 0 map between the localization algebra and row algebra. So you just take the value at 0 for each path. So this is evaluation at 0 map. And because this evaluation at 0 map is a star homomorphism. So it induces a homomorphism on the K-theory level. And actually, when we define the row algebra, we require ZD is contained in ZD prime when D is smaller than D prime. So we will have the direct limit system of those row algebras. So we can consider all the D. We use inductor limit over D. And if this evaluation at 0 map for all the D, so we consider about the inductor limit to put them all together. If this is called a Baum-Connes assembly map. If this is injective, then we will say the strong conjecture holds for gamma. And if it is isomorphism, we will say the Baum-Connes conjecture holds for gamma. And so strong local conjecture implies Novikov conjecture. So in my talk, we just focus on the strong Novikov conjecture. So if we can prove the for the given short exact sequence of countable discrete group, and assuming normal subgroup and quotient group are causally embeddable into Hilbert space, then the strong Novikov conjecture holds for G. So we can prove the strong Novikov conjecture. And then as a result, the Novikov conjecture holds for G. Okay, so in order to consider about the geometry of the normal subgroup and quotient group, we will define the system algebra associated with infinite dimensional Euclidean spaces. So if you have an infinite dimensional Euclidean space, we will consider about all the finite dimensional affine subspaces and take E alpha 0 be the linear subspace of E consisting of differences between pairs in E alpha, and then we can define system algebra of all the continuous function from E alpha to the complexified Clifford algebra vanishing at infinity. So and we will take the A of EA to be the suspension, to be the graded. To be the suspension of this system algebra, but we have to be careful. We don't take we will consider about the grading on this system algebra and the C0 of R. The grading on C0 of R is given by the odd and the even functions, and the grading on C of EA is given by the odd odd part and the even part of this Clifford algebra. And also, if you have any if you have any pairs of EA and EB, so EA is included in EB, and then we will have a decomposition for EB, and such a decomposition will give you an inclusion from this system algebra to this system algebra. Oh, excuse me, this is A, and this was given by take the functional calculus some essentially self-adjoint unbounded operator, and times with one graded tensor with the extension of H. And then there is we will consider about the system algebra associated with the infinite dimensional Euclidean space as a inductive limit of all those all those system algebra. And the inductive limit is taken over all the finite dimensional affine subspaces. So if we have a group Coarse embedding into Hilbert space, we can define the system algebra to encode the geometry of the group. So if you have the Coarse embedding of the quotient group, then we will find a complex space X with the quotient group action, such that for each finite subgroup, X is F contractible, and the transformation group part is AT meanable. So here essentially this construction is due to Professor Hickson. So here it's contractible just because it's some complex space of the probability measures. And also, let me explain what's the meaning of AT meanability. So here, if you have the group action of the quotient group on X, then you will have transformation group height, and the group height has a function on the transformation group height is called a CN conditional negative definite function. Means that if you find any finite element on X and any element on the group gamma, you will have sorry, maybe I should write down here. You will have phi xi gi inverse gj. Sorry, it should be like, excuse me, gi gj, and lambda j. If you take summation of ij, this is smaller than or equal to 0. So lambda I is real numbers with summation equal to 0. This is CND. And if this map is proper, if this is a proper map, then we will call this conditional negative definite function is proper. And a transformation group height is called AT meanable if it has a proper conditional negative definite function. So the definition of the concept of AT meanability was introduced by Tu. And he has a result if you have a transformation group height and it has AT meanable, then we can define a continuous field of Hilbert space with a proper G module N action. Excuse me, this is a typo. So here we by Tu's result we can have a continuous field of Hilbert space. So which means we have a fiber bundle over the complex space X, and each fiber is a Hilbert space. And by the construction of Higgs-Gasparov-Trott, we can define a system algebra on each fiber, and we can define a continuous field construction of on this fiber of system algebra, and consider about all the continuous sections will give us a system algebra with the quotient group action, and we can also show that this action is proper. So we will use this system algebra to encode the geometry of G module N. And also for the normal subgroup, if the normal subgroup is closely embeddable, then we can also find a compact space. So with the same properties, but here we need a little bit more. So here Y not just have n action. We extend the action to G. We have a G action, but we don't know the property of G action on Y. But we know for each finite subgroup of G, Y is F contractible. And also for each group n prime containing n with finite index, the transformation groupoid is AT-meanable. So here we define the compact space with G action, not just n action. Okay, so we will use the two famous result by two. If you have a étale groupoid, the étale groupoid has AT-meanable, then the Baum-Connes conjecture holds for G. And I would like to point out the Baum-Connes conjecture for the transformation groupoid is actually equivalent to the Baum-Connes conjecture with coefficient in C of Y for the group n prime. Okay, so now let's look how do I will give a brief proof for my result by using two's result. So in order to consider about encode the geometry of n and G module n, we can consider we will define a twisted row algebra and also a twisted localization algebra. So here the twisted row algebra is you can view this as a definition of the usual row algebra, but we put some condition on the about the twisting to encode the geometry of the normal group and the quotient group, and also by the cutting and pasting machinery, we will say if this group, if the normal group and the quotient group are cross-embeddable, then such a twisted assembly map is isomorphism. So here we actually prove a twisted version of Baum-Connes conjecture. And next we will drop off the coefficient. So actually we can define a fiber-wise bot map, and then by the fiber-wise bot map, by a result of Higgs and Gasparov and Trott, they show that if you have you can define for infinite dimensional Hilbert space, you actually can prove you actually can construct a bot map from the continuous function on R to the sister algebra we defined before. This induces isomorphism on K-theory level. So actually, for each fiber, so we can define a fiber-wise bot map. Actually, it's like X times Y with the trivial fiber with a trivial bundle with fiber S to the C of X and times A of Y of H. Oh, let me check. Oh, sorry. This I should switch the X and Y. This is X, and this is Y. So we can generalize the definition of row of the bot map to a fiber bundle case. So each fiber is actually a copy of S here, and each fiber of this guy is actually a copy of A of E. So we all show. So actually, we can show this induces isomorphism on the localization part. So as a result, we will show this. We will have the assembly map with coefficient case. And now we use this fiber-wise bot map to reduce it to reduce the twisted Baum-Connes conjecture to the Baum-Connes conjecture with coefficient on C of Y times X. So actually, this is not just the injective. This is actually isomorphism. But we just need the injectivity. Okay, so and also by a decent principle, that's also called a decent principle. So this is then we can reduce, we can drop this coefficient, and we will get the strong Novikov conjecture for the extension G. Okay, so maybe I should stop here. Thank you.
Thank you.
So, any question?
Yes, do you have any? Okay, Heath.
Oh yeah, could you review what you said in the very last couple of slides about something being actually an isomorphism?
Here?
Yeah, you said one of these maps is not just injective; it's an isomorphism. Could you just say that again?
Yeah. So actually, we can define a favorite bot map, and we will show we can show this is injective just because we will have the map from the key theory of CL star PD of G. So here this is CX CY times X. So the suspension of this guy is actually isomorphism to, this is by the favorized bot map. So actually I need G. Or maybe G is actually given by here. So this is isomorphism, and then we will have, this is injective. This is just like we.
Oh, I see. Yeah, thanks.
Yeah. So actually here this is isomorphism just because both groups are topological. You can do the cut and pasting on the Rips complex.
Yeah.
Okay, so any other questions or comments?
Yeah, I have a question.
Yes, please.
You mentioned that G doesn't have to be uniformly embeddable by these fancy examples, but it seems to me your proof is using some kind of geometric property of the group G, that it acts on some bundle of Hilbert spaces in an affine way, something like that. Can you make a precise statement about what the geometric property of G is that makes this argument work?
Oh, yeah, this is a good question. So in order to prove this twisting of this twisted Baum-Connes conjecture, we actually use this, because this is algebra encode the geometry of the quotient group.
Mm-hmm.
So because of the definition of this row algebra, actually the localization algebra and the row algebra, we can actually do the cut and pasting on the Rips complex of G, but we will have some so we will cover the Rips complex of G with some disjoint union like the Rips complex of the coset. So sorry, I need and this there has some shift. Maybe I should put maybe just we don't have to worry about the Rips complex. Just decompose the G as the coset of as those cosets, and each of them is actually a copy of N.
Mm-hmm.
So which means if we decompose the root algebra and localization algebra by the geometry of the quotient group, actually we have a bunch of Baum-Connes conjecture with coefficient for n for the normal subgroup.
Okay.
Yeah, and actually by the two's result, we'll see the Baum-Connes conjecture for the n with coefficient in those continuous functions holds for n. So which means we do the cutting and pasting. We cut the Rips complex of G into a lot of pieces of the Rips complex of n, and because of the invariant, because of the definition of equivalent root algebra and localization algebra, we will say actually it's a bunch of fibers of a bunch of Baum-Connes conjecture for n, and since they are invariant, so actually we just consider about those fibers. Is each of them is actually one n here. So you can view this as G, and each of them is actually a copy of n. Actually, they are just some cosets, but actually you can use a group action, shift those fibers to a single one, or finite many of them uniformly.
I was hoping for some, I mean, what you're describing is how the proof goes, but I was hoping for just some summary property that G might have, something less than uniform embeddability, so that in fact maybe you could prove the Novikov for some groups with some property less than but related to uniform embeddability. But I guess it's not that clean.
I don't think so. Yeah, So actually, we have some results in this direction. Just we are still working on it. Of what about if we take finitely many extension of the cos-embeddable groups, and we also consider about the inductor limit. So we consider about such a class of group. And we can consider, we can show Novikov conjecture holds for every element in such a class generated by cos-embeddable groups. Yeah. So but I don't know what geometric property of G contribute to the Novikov conjecture. Yeah.
Okay. Thank you.
Okay, thank you.
Just one other question. Is property A invariant under group extensions?
Yeah, I think so.
Oh, okay.
Okay. Do you have any other questions or comments? Okay, there's no message in chat. Okay, let's thank Jintao again for a beautiful talk.
Okay, thank you.